A very quick synopsis.
Soup would be kind of weird. Soup would kind of like pour out.
A little, but not really.
Yeah. Get the spoon part.
I mean,
Of the
you just do it
MCR,
like
in
that,
case
like-
this is of interest or use, kind of a neat, brilliant idea I came up with. Was color coding the positives and negatives. So, we've got two linear functions. We're using red for positive, just like your jumper cables, and blue for negative, which is pretty standard, okay? So we have two graphs, a graph of our f of x function, this one here, and a graph of our g of x function. So we colored the f of x function red where it was positive, and blue where it was negative. And we colored the g of x function blue where it was negative and red where it was positive. So that below the axis, both of our functions are blue, for reasons that should be really clear. Okay? Above the axis, they're both red. Then, we color-coded the x-axis according to whether the product, f of x times g of x, was positive or negative. Very easy to see that up to this point, we have a negative, and we have a blue function here and a red section of this function here, right? So just visually, we see, well, for this interval, we have a red and a blue, a positive and a negative, so that the product is negative. So we take that interval and make it blue, okay? Similarly, for this interval here, past this 0 of the g of x function, the f of x is positive, the g of x is negative. Red, blue. Well, positive, negative gives us a negative, right?
Really?
Okay. Then, between here and here, well, both functions are positive. They're both above the axis, and of course, they're both colored red to remind us of that. And when we multiply the two functions, then we're multiplying two positives, so on this interval, the product is positive, okay? Now there's some more subtle aspects of this graph. So I then asked people to draw a graph of the product function. A couple of people drew graphs that looked like this purple graph here, okay? What's wrong with that purple graph? So far there's nothing wrong with it. It's negative where it's supposed to be negative. That is, on this interval, well, that's negative, right? Between here and here, it's positive, and then between here and here, it's negative, right? But what's going to go wrong?
It's gonna get positive.
Yeah, I mean, if it's doing this, it's going to hit 0, which it can't do, because f of x isn't 0 and g of x isn't 0. This can't be 0, right? The product can't be 0. The only way the product can be 0 is for f of x to be 0 or g of x to be 0. You can't multiply two non-zero numbers and get 0. We have to understand that about the numbers, and then put that, use that understanding and understanding what it tells us about the graphs, okay? So over here, we're headed right toward a 0, which we can't have. Not only that, we're headed into the positive, which can't be. Because this thing's going to stay positive, and this thing's going to stay negative as we move this way, right? And similarly, this thing's going to stay negative, and this thing's going to stay positive all the way from here to infinity, right? Okay? So we got to understand that. So this graph can't possibly work, although it looks a lot like some of the graphs that I ended with last time, so it was a good thing to have an image of. A lot of polynomial graphs will look like this. Okay, but not this one. Okay? So another thing we reason out is, as we go this way, what's happening to the f of x values? They're getting bigger, right? And what's happening to the g of x? Well, those are the g of x values. What's happening to the f of x values? Well, they're negative, but they're getting bigger. They're bigger and bigger negatives, right? So what happens when you multiply something that's getting bigger by something that's getting bigger?
It's gonna get bigger.
It gets bigger. Okay?
Bigger.
It gets bigger, faster, and faster. Because you're multiplying bigger and bigger numbers by bigger and bigger numbers. So the thing has to do this. It has to start going really fast into the negatives. Over here, well, it's the same thing. This one's a bigger and bigger positive. This one's a bigger and bigger negative. So as you go this way, it's still negative. You multiply a positive by a negative. You got to get really big, okay, pretty fast. That means that our accurate graph, well, the graph has to go through 0 when either of these goes through 0. Hopefully we understand why that is. Because if one of these is 0, the product is 0. So we have zeros here and here. Then the question arose, well, wouldn't this thing peak where these two graphs cross? It's a reasonable thing to think, okay? But it doesn't work out that way. So we went to some trouble to show, well, if I multiply a linear function by a linear function, what kind of a function do I get? And if you're in the MCR, don't answer that. Somebody else. If I multiply a linear function by a linear function, what kind of function do I get? You get a quadratic function. Now we proved that because if f of x and g of x are both linear, then f of x is in the form mx plus b and g of x is in the form mx plus b. But you have different m's and different b's, so I say m1x plus b1, m2x plus b2. So h of x would be the product, well, it's f of x times g of x, so here it is. Well, how do we multiply these? We use the distributive law. We don't use that F word thing. Okay? Because we have to know how to use the distributive law and we don't want to shortcut it. Okay? Now when we start factoring things, maybe that thing that I don't like could be useful for factoring trinomials. Okay? There's a point to it, but other than that, you should never use it. You should always use a distributive law to remind yourself, because I find that even though people have this mastered 2 months ago, they don't always have it mastered now. Okay? Especially if you've got to apply it to a symbolic function like this. Well, I'm not going through the details, but when we multiply these, we get h of x is m1 m2x squared plus m1 b2 plus m2 b1x plus b1 b2. Something that's easy to work out. You just use the distributive law and be careful, like I was. I mean, yeah, wrote down an m1 here accidentally, and when I got down here, it wasn't behaving itself. Okay? So you got to know whether it's behaving itself or not. That takes a little bit of insight. Okay, well, anyhow, that function is quadratic. It's of the form ax squared plus bx plus c with a equal to m1 m2, b equal to m1 b2 plus m2 b1, and c equal to b1 b2, which I wrote down here. Okay? Now, what do you know about the graph of a quadratic function? It's a parabola, right?
Yeah.
And what do you know about parabolas? It's a parabola that opens upward or downward in this case. What do you know about parabolas that open upward and downward?
Maximum or minimum.
It's got a maximum or a minimum. If it opens upward, it's got a minimum. If it opens downward, it's got a maximum. That's important. The vertex is important. What's another important characteristic?
Axis of symmetry.
The axis of symmetry. Okay? Now, where is the axis of symmetry?
Right in the middle of the graph.
Again? Middle of the graph, right? It's the axis that splits the graph in two equal halves. So it's going to look like this. Now, exactly where is that in terms of the characteristics of the f of x and g of x functions? Where do you find the axis of symmetry?
Wherever I just say like make it simple, like wherever you can split it and like it looks
Yeah, but in terms of the f of x and g of x functions, well, somebody said, well, it should be where the two graphs cross. Well, that's reasonable, but it doesn't work out. Why? Because if it's symmetric, then the axis of symmetry has to go halfway between the two zeros. Otherwise, one of the zeros will be closer than the other, and you're not going to have symmetry, right? Well, that brings together a lot of characteristics, and you know the algebraic characteristics. People want to say, well, it's at negative b over 2a. Well, I want you to know that, okay? But I want you to relate it to the basic characteristics of the graph, because that's where you get deep insight and deeper ability to use your mathematics, okay? And understand graphs specifically, but even more important, gives you an ability to think a little deeper, okay? So there are a lot of benefits to what we're doing here. And I hope it'll work out, we'll see. If I come up with the right problems and you do them, and you learn what I want you to learn, and you know, it's on me to come up with the right problems. Okay, well, anyhow, that's what we learned from this, okay?